In this next exercise, we will examine this function. The first interesting thing we see is this square root of x squared, which we have to be very careful because the square root of x squared isn't simply x, but it is the absolute value of x, meaning it is x if x is at least 0, and negative x if x is less than 0. Now we can rewrite our function with these cases, giving us g of x equals x times e to the negative x squared over 2 if x is at least 0, and negative x times e to the negative x squared over 2 if x is less than 0. And now we can see that despite the square root, our function is defined on the entire number line. So our domain will look just like this. Next, we will have to find the derivative of this function. However, the absolute value function can be a bit strange around 0, so we must find a derivative at that point by definition. The quotient of differences will be g of x minus g of 0 over x minus 0, which is simply g of x over x, since g of 0 is clearly 0. This will be, with our cases, e to the negative x squared over 2 if x is greater than 0. Since we divide by x, we cannot divide by 0, so we must leave it out of the domain, and it will be negative e to the x squared over 2 if x is less than 0. Now to find the limits at 0, if we go to 0 from the positive side, we have this limit as 1, and if we go to 0 from the negative side, we have this limit as negative 1. And we can see that since these two values do not match, the limit doesn't exist, so the function is not differentiable at the point 0, which means that 0 will be a critical point. But on the rest of the domain, we can easily differentiate the function, so we can calculate g prime of x, giving us e to the negative x squared over 2 plus x times negative x times e to the negative x squared over 2 if x is greater than 0. Again, we already seen the 0 case, and it will be negative 1 times this if x is less than 0. Minus x now, to find the critical points, we can factor out this from both functions, giving us e to the negative x squared over 2 times 1 minus x squared if x is greater than 0, and of course negative 1 times this, so minus e to the negative x squared over 2 times 1 minus x squared if x is less than 0. Now we have to find the zeros of this function, which will be quite easy since this is positive, this is also positive, negative one is negative, so we only need to find the zeros of this factor, which is the same in both functions. So we must solve 1 minus x squared equals 0, which gives us x equals plus or minus 1. Of course, x equals 1 will be in this part as a critical point, and x equals negative 1 will be in this part, and we can also graph our critical points, with 1 being around here, negative 1 being around here. Now we can make our table. With our intervals, and we will have, of course, g prime and g, and our intervals will make our table look something like this. Now we have the critical points. At negative 1, our derivative is 0. At 0, our derivative does not exist. And at 1, it is 0 yet again. Now we have to fill out this first row. And to do that, we need to find the sign of the derivative function. And we can see that we know the sign of everything except this factor. So, to find that, we should graph this function. We already have the zeros of that function, being 1 and negative 1. And we can see that this is a second degree polynomial, and it has negative x squared. So it will be a depressed parabola, looking something like this. And now we have everything to find our signs in the table. So, looking at our first interval, which is x is less than 0, less than negative 1, sorry. Here we have this function, this bottom one, and we can see that our interesting part is negative over here. So we have negative times negative, giving us a positive derivative on this first interval. On our second interval, we are between negative 1 and 0. Yet again, we have this function, with our interesting part being positive here. So we have negative, positive, positive, the function being negative here. On the next interval between 0 and 1, we must be very careful because we have to use the upper function in this case, with our interesting part being positive. So we have positive times positive, giving us positive derivative. And our last interval after 1, we are yet again in this row, with our interesting part being negative. Positive times negative is obviously negative. And now we have everything to find where our original function is increasing or decreasing. Using our rule, it's obvious that our original function is increasing here, decreasing here, increasing here, decreasing here. And now we are finished with our original exercise. However, we can quite easily tell where it has local minimums and maximums. By connecting these arrows like this, we can see that it has a local maximum here, a local minimum here, and a local maximum here.